Right, let's start. So last time, we discussed about several different methods to compute the least square solution. Okay, so we can use it through the QR decomposition and the normal equation, and also this SVD. Okay, so in the case of an SVD, the first step of computing the SVD of obtaining U sigma V transpose, and then once we obtain them, and then the rest of the process to compute the solution for this least squares is quite simple. It's just a simple matrix or matrix vector product like 3 times. But as I mentioned, computing the SVD is the most expensive operation among the other methods that we can solve least squares problem. And then let's move to chapter 8 about this floating point arithmetic. So here okay, so this floating point numbers or floating point arithmetic is about the representation of the numbers, and also the the way of computations of maybe adding, subtracting, and multiplication and division using the numbers represented in our computer. And the main limitation of representing the number in our computer is to use the limited number of bits. So if we call our computer as 64-bit computer, and then it means it can represent any given number by using this 64 number of binary values. And so in that case, we use this kind of floating point representation of the numbers. So suppose we have only like 10 bits of binary values to represent a particular number, and this particular number of bits or binary values is fixed in advance. If we define it as maybe double or long or integer and so on, and in that case it will assign the fixed number of bits to represent a particular number. And then this is one representation that we are currently use, and we basically assign 10 binary values to represent the sign of the numbers, and also maybe we will use a 1 bit over here, and then maybe 4 bit to represent this number called a significant, and then we have a particular base which is usually represented as 2, and then we have some exponents to represent this exponent value by using the rest of the bits that we have. So we use the 5 bits, and so we can use another 5 bits to represent this exponent part in our number. Okay, so if we sometimes download some data files represented as a CSV format or any other ASCII file formats, and then sometimes if we open some of these text or ASCII based files, and then those feature values in the maybe in some of the data sets can be stored as maybe 3.149, and so suppose this one is the feature value 1 and the feature value 2 and so on, and then 3.145 and then 0.0013 and so on, right? So in this case we are currently using the fixed point representation, because in this case, yeah, we didn't use this floating. Yeah, I mean this is not certainly a floating point number operation. And then yeah, in the case of a floating point number operation, in this case we just represent it as this form: 1.3 and e and negative, something like this. Okay, so if you just open some of the data files, and then you will sometimes see this kind of representation to represent a particular number. And so in this case we are representing this same number in this form. Okay, so this is called significant, and this is called exponent. Okay, and also this is called our basis. And in this case, yeah, let's just think of this pros and cons of representing the number in this fixed point or this floating point number representation. So in this case, yeah, suppose our number is really small, like in this case. Okay, so in this case, all of these numbers of leading zeros and 0 point and 0, 0, 0, 0, and these numbers will occupy our memory. So in the ASCII based file, each of these characters, I mean they are really the characters when storing it as a ASCII based file, and then it will just use 8 bits, for example. Okay, so in this case we have to use our many number of bits to represent all these 0 numbers. So this can also happen when representing really big numbers, like in this case. Okay, so in this case we have to use all the bits or many of these bits to represent this all 0 numbers, which is not much meaningful. So in this case, more efficient representation can be in this floating point number representation. So in this case, we only store the meaningful number of bits. I mean the meaningful number of those digits, and also we store how many we have to, how many digit points that we have to jump or move this decimal point. Okay, so in this case, in this case 1, 2, 3, 4, 5, 6. So we need a 6 character, but in this case 1, 2, 3, and 4, 5. Okay, so in this case it is also having 6 characters, but we don't actually need to store this E and also those numbers as well. So I will give a more detailed example, but anyways you get the idea of this advantage of this floating point number. Okay, because we can avoid storing those unnecessary zeros on the left part or the right part. Okay, so this is our floating point number, and so in this case, as I mentioned, it can have a both positive or the negative sign. And so in the previous case of using or assigning or allocating these 10 bits to store these numbers, so we use 1 bit to represent the sign, and then some of these are 4 bits to represent this significant and exponent. And because our computer is using binary number, we usually use this base as 2. Okay, and also what about these significant? So in the case of this significant, in case of using this decimal numbers, and then this significant can be maybe 9.674 and so on. And so all these 3 numbers are significant digits or the numbers that we have to store. But in the case of the binary number representation, and then let's think of let's think of this number, for example, in a binary number case. And in this case, we can represent this number as 1.011 times 2 to the power of -5, right? So we have to store these numbers and also this exponent number. Okay, so in this case, the significant digits that we see in the case of this binary number representation, the first digit will be always 1, right? Because if it is 0, okay, if it is 0, and then we can always move it to, the decimal point to the right, and then we add, we subtract this exponent by 1. Right? Okay, so the first digit is always fixed as 1, and then we can use our bits to represent the remaining numbers after the decimal point. Okay. Okay, so this is basically the binary number representation using this floating point. Yeah, so in general, when using the base as beta, and then this floating point number representation can be represented in this form. So plus minus, that indicates the sign, and then this one is the first significant number, and this one will correspond to like D0 and D1, D2, and so on, right? And so this one is the digit of 1, right? And then this one is like digit of beta to the power of 1, and beta to the power of -1. Okay, so this is representing our significant number, or significant, and then times beta to the power of this exponent. Okay. So in this case, when using this binary number that uses the base as 2, and let's assume that we use 4 digits to represent our significant, and then it means, in the case of binary number, this D0 is always fixed as 1, so we don't need to actually use our limited bits to represent this D0, and so we always assume that the first digit is 1, and then if we use 4 bits to represent this significant, and then that 4 bits will be used to represent or store those 4 numbers, right? And so in this case, it means that we can represent this significant numbers up to this 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, and 2 to the power of 4. Okay, so this this can be viewed as our precision, or the accuracy of representing the number. And so it means that we are ignoring the numbers appearing after those 4 digits, or those 4 numbers, okay? Because we do not store them. Okay, and then also we have this part. So here, using this significant, and then 2 to the power of some value e, and we represent this exponent e by using 5 bits, right? This 5 bits. And so if we think of this 5 bits in a binary number case, and then yeah, it is representing 0, and it is representing is it this number, right? Okay, so in this case, yeah, we can represent 32 different numbers by using 5 bits, and using that 5 bits we want to represent this e, right? And so we can actually so this e is basically some integer value, and that integer value is originally ranging from negative infinity to infinity, but we only have the capability to represent those 32 different numbers, and so we have to map this 32 different numbers to some range in this infinitely large kind of ranges of these values. Okay, so one of the reasonable choice is including 0, and then like this representation. Okay, so in case of a negative 15, and then we map this is 0 0 0 0 0 like the smallest possible number into some of these negative exponent, and then 1 1 1 1 1 as this number. Okay, or it can be like this range, but anyways, yeah, we can have this particular range centered as 0 to represent this exponent by using this finite number of bits that we assigned. Okay, so in that case we can specify or denote this range of this exponent as e minimum or e maximum. Okay, so in this particular case it is corresponding to negative 16 and 15. Okay, so this is the floating point number representation, and then here there is an important notion of this machine epsilon, or sometimes it is called machine precision. Okay, machine precision. Okay, so the meaning of it is, given this particular number, so we add or subtract, or we basically add it in general. So we have basically some true number x, and we just consider the number that adds this machine precision with the original value of an x, and then when representing these two numbers by using our floating point number representation, so let's call it as this. Okay, so what that means is, like, so suppose we have this number, but in a decimal point, and then let's use it. Let's use the floating point number representation that uses maybe 4 digits as our significand, and then in this case 1.3489 and 10 to the power of maybe 1. Okay. So this will be our exponent, and then this will be our significand. Okay, so in this case we threw away this value, right? So those minor values are gone actually. So to represent this particular number by using the floating point number representation, by use that anyways uses the fixed number of bits. Okay, so in this case, if we add over here at this particular digit, even if we use it, even if we replace it as maybe 7 or 3 and so on, and then once representing it as a floating point number, and then those two numbers will become exactly the same, right? So this machine precision is like, this number is basically the maximum possible number. Okay, so the maximum possible number when adding to the original number, and then the floating point number representation doesn't actually differentiate them. Okay, so when representing it as this floating point number representation, and then they look exactly the same from the perspective, from the computer's perspective. So that is the definition of this machine precision. Okay, but this machine precision, in this particular case, we can easily see that the machine precision is just right after the number of digits that we can use for this significand, right? So the maximum possible number here is like this number, I mean at this particular digit position, right? But when representing this number, given a different number given different original numbers, and then this machine precision can become different. So for example, so in this case, because we can represent up to this 5 digits of 1.3564 times 10 to the power of 6, right? So this is the floating point number representation, and so the machine precision will correspond to the number having some value over here at this particular digit position, like maybe 10. Okay, so in this particular number, the machine precision could be viewed as 10, but in this particular case, it will be 0.10, like this number, right? So it means that depending on the original value, this is smallest, I mean the maximum possible number that the computer cannot differentiate can vary, or can be dependent on this original number. Okay, so let's see. 네. 네. Okay, so in this case, the machine precision is actually defined as some relative number. Okay, so in the previous case, so you can understand that those machine precision can vary depending on the original number, and so this machine precision is actually defined in this form. So it means that we are dividing those the maximum possible number that cannot be differentiated by our model. So we divide that number by the original value of yeah, yeah, and so so that is our machine precision, and so it can be represented in this form, which means, so if we have a this kind of representation that uses, so here how many number of bits we use to represent this significant. So it's beta to the power of 0 corresponding to this number, all the way to the negative beta to the power of p minus 1, and so starting with the 0 and the p minus 1, and so we have in total p digits to represent this significant, right? Okay, so this is the maximum possible, the minimum possible digits that we can represent, and so the numbers that appears after this digit will be ignored or cannot be differentiated by our model, right? And so in this case, we can represent the number that is right after this minimum possible kind of digits into this form. So we have the beta as our basis. So like this is the maximum possible number, right? And so we typically just multiply 0.5, for example. So in this case, so this is exactly like the half of this minimum possible value, and then that means like, so if we in the case of a decimal point, and then let's see. So in this case, so we can we can have a freedom to add some numbers at this particular position, but this number can be 10 or 30 or 90 and 70 and so on, right? So in this case, we just conveniently define the half the number. I mean, so like the machine precision in this particular case, or the maximum possible number that when added, which cannot be differentiated as this number, right? So in that case, it can be represented as this number, like 100 by 0.5, right? And this number is corresponding to beta to the power of negative p minus 1. Okay. So that way, it's like, this is the same as negative p minus 1 for the exponent. Okay, so you guys now understand the definition of this machine precision as this relative difference that cannot be differentiated by our machine. So in this case, we can understand also that our machine can view those numbers lying in this continuous domain as some of these discretized value. Okay, discretized value. So discretized value means like, so in this case, we are just representing it as 1.343564, for example, and then if it is like 5 and 1/7 and so on, and then it will be represented as 1.3565 and so on, right? So those two numbers will be different because this digit became finally different, but as we know, the difference or the variation after this minimum possible number will not be differentiated by our machine. So in this case, we can think of this discretized level of our continuous numbers, so in this form. So yeah, when using the exponent as, for example, 0, and then in this case, and then suppose we can we can represent this as significant by up to like this position. Okay, so in this case, the discretization level or the difference is something like this, right? So this is the level of discretization, and so to represent a different number from this, and then the next number that we can represent is this. Oops. Right? That has relatively like the difference, having the difference of like this one, right? Okay, so this is the amount of the discretization that we use when using the exponent as 0. But what if we use the exponent as 1? So in this case, between these two numbers, now the gap between these two discretized number has now become like 0.0001 is the difference between these two numbers. But this number is actually multiplied with our exponent, and so yeah, it actually has the discretization level of this number that is much larger than this number, discretization number, when using smaller exponent, right? Okay, so this floating number representation actually discretizes our numbers in this continuous domain in this form. So when the number is really small, that have the small exponent values, and then the discretization level is much tight or much fine-grained. Okay, but this discretization will be much more coarse as we represent the larger and larger numbers. Okay. Okay, so that is one of the main characteristics of this floating point number representation. Okay, so that actually gives the some of the flexibility of representing the numbers using the finite number of bits. So in this case, let me give the alternative method of representing the numbers, which is called fixed point number representation. So we currently study the floating point number representation. In this case, fixed point representation, for example. Okay, so this is the opposite case or opposite strategy to represent the number. So in this case, yeah, basically, yeah, let's use maybe let's use maybe 10 digits, 10 bits of the numbers, for example, to represent a single number, and then literally the smallest possible number is all 0, for example, and then all ones, right? So if we use 10 bits, and then it will represent 0, and then it will represent 1023, right? So we have in total 1024 different numbers, and then let's just take it as just a little number that we see, and then we can maybe assign some decimal point in a particular position. So in this case, for example, let's put the negative sign over the decimal point over here, and also we want to be able to represent the sign of this number, and so let's just add one more bits to represent the sign. Okay, so in this case we have positive and negative numbers that is assigned by additional bits. So in this case we can represent the numbers ranging from negative 1023 up to 1023. Okay, so in this case, if we assign the decimal point over here, and then what is the range of the numbers that we can represent? In this case, we are using 7 bits, the first 7 bits, and then the rest of these the 3 bits to represent the numbers below this decimal point. Okay, so it's like okay, so I'm not gonna try to convert it into the actually this number, but I'm gonna represent it as this. So we have 7 ones and this guy, and also positive 7 ones and then 0.111, and in the middle we have all zeros, right? So we still have a 7 digits and 3 digits after this decimal point, right? So this will be the range of the numbers that we can represent by using or by applying this fixed number representation, right? So in this case, the main point is that we assume that the decimal point is fixed at the particular position, and then we don't actually use this floating point number representation. Okay. Okay, so in this case, what will be our discretization along this continuous value domain? So in this case, it will have all these uniform kind of interval, right? So we will have this uniform interval, and this minimum point is this guy, and the maximum point is this guy, right? So this one is approximately like negative 127 or negative 128, for example, and this guy is 128, for example. So when using this fixed point representation, and then outside of this range, we cannot represent the numbers smaller or larger than those 2 values. So we have quite limited limited the range of representing the numbers. Okay, and then how can we widen this possible range of numbers that we can represent? Okay, so in this case, we can just by using the still the same number of bits, and in that case, we can just move this decimal point over here, for example. Okay, so in this case, we can represent the numbers between negative 512 and positive 512, right? And so this number will be negative 512, and this number will be positive 512. Okay, but what's the drawback in this case? After widening this range of the numbers that we can represent, but this discretization level became much coarser, right? So in this case, if we move the decimal point over here, and then we cannot represent the difference appearing at this particular position, right? So we are using the larger discretization levels. Okay, so this kind of discretization is inevitable because simply because we are using the fixed or limited number of bits, right? So we cannot, it is impossible to represent this continuous numbers by using the fixed number of bits. But here the strategy is different. So in this case, regardless of the particular sub-ranges of our numbers, we are using just a uniform gap or uniform interval for our discretization level. But in this case of floating point number representation, when representing the small number, and then we adaptively use the small interval when representing the relatively large number, for those subregions that we can represent, and then we relatively use larger intervals. Okay, so in this case, one advantage of using this adaptive interval is to extend the possible ranges of the numbers that we can represent. Okay, so in this particular case, then it may not be that much important to differentiate like really large numbers. So when dealing with for example, maybe some of these are large numbers, and then here if we just stick to the different the interval of our discretization fixed at maybe below some of the decimal point. Okay, so in that case, because it is a really large number, so we can maybe coarsen or increase the interval, okay, to be able to represent this number. So maybe this floating point number representation may make more sense in practice, and also it has relatively large number, large range of the numbers that we can represent. Okay, so this is one kind of advantage of this floating point number representation. And also let me discuss about the practical issues when performing some arithmetic operations by using those two different number representation. So when using the floating point number representation, for example, one of the arithmetic of an addition. Okay, so in that case, let's imagine how we can perform this addition of these two floating number representations. So for example, okay, so initially we are given these two different numbers, and then let's perform the addition of these two numbers. And then when adding these two numbers, how do we add them? And so we will first move the original decimal point by reflecting this exponent like this, right? And 1356.4, and then also we will do the same thing, right? And then we will just align our decimal points like this, and then so it's 32158, right? And once aligning this decimal point by reflecting this exponent value of these two different numbers, and then finally we perform this addition, right? 1, 3, and 8, and 8, and 5, 5, 8. Okay. So in this case, we now convert it back to our floating point number representation of 13885 times 10 to the power of 3, right? So yeah, this is how we perform the addition of our two floating number representation. And then what about the fixed number representation? So okay, so let's see. So if we allow the 5 digits before the decimal point, and then 2 digits after the decimal point, and then yeah, where is 7, 8? Yeah. So the first number, let's see. Yeah, the first number is represented as this one, right? So this one will be the fixed number representation, and the second number, fixed number representation will be like this, right? So initially the two numbers are stored in that manner. So when adding them together, we don't actually need to align those decimal points like this, right? We can just simply add those two numbers because they are already aligned in the case of fixed point representation, right? So this addition becomes much simpler, and also subtraction follows the same scenario. Okay, but what about the division and the multiplication? So in the case of division and multiplication, this floating point number representation may become kind of slightly simpler than the fixed point representation, because I mean it's just a minor difference, and so their computational cost will be almost the same. But yeah, let's think of this multiplication between these two numbers, and then in this case, yeah, we can just multiply those two numbers. Okay, and then I'm not gonna compute this exactly, but maybe 3.7 or something like that. Okay, and then how about handling this exponent? We can just simply add those two exponent numbers, right? So if it was -1, and then we can also add these two numbers, resulting in 2 as our exponent, right? So in the case of multiplication or also division, in the case of division of this number by this, and then we can just simply subtract this exponent, right? And then we can do our own division between these two numbers. And so in the case of multiplication and division, this significant and also exponent can be handled just separately, which is really convenient, right? And also in the case of fixed number representation, the multiplication and the division, it's not much. Not much difficult compared to this floating point number. So if we just multiply these two, and then we just keep multiplying them together, and then we just simply count okay, so it's so it has to move like this and move like this, and then we can kind of imagine that those two numbers that start with the first digit just before the decimal point, right? Like this kind of representation, right? And then we can just simply compute those count when representing it as this floating point number representation, and then we just do some post-processing of moving some of these decimal points after just multiplying these two numbers separately. So although I didn't give full details about how to perform multiplication and division in this floating point and also fixed point representation, but yeah, the main kind of message, or at a high level, you can think that this floating point representation, the computational cost of this floating point representation is much more expensive than the fixed number representation, okay, because of this additional aligning step of this decimal point. Okay, and this kind of a fixed point representation is actually used in some of the low-powered CPUs or embedded systems. So in the case of maybe Intel CPUs or maybe our NVIDIA GPUs or AMD CPUs, they all use, mainly they use this floating point representation. Okay, but in some of the low-powered CPUs, like maybe the CPU that is embedded in our smartwatch or maybe Fitbit, which requires like a small limited battery and also like limited computing powers. And in that case, to just simplify this arithmetic operations of adding addition, subtraction, and multiplication and division, they sometimes adopt this fixed point representation. Okay. Any questions so far? Okay. And also this fixed point representation, although this is not directly used, directly related to this fixed point representation, but we can, these kind of techniques can also be used in compressing some of the neural nets and any other machine learning techniques. So in that case, there exists a literature called model compression. So in this case, there are various different techniques, but one of them is called ternary compression or representation of these numbers. So in the case of ternary representation, when storing or handling the model parameters, for example, when multiplying some of the given vectors with the linear transformation matrix W, okay, and each number existing in our W will be represented by default. They will be represented as the floating point. And then if we use them as a fixed point representation, and then their computations might be simpler. And even further, we can represent each of these numbers as just, did I explain this already in the previous class? Probably not, right? Okay, so in the case of this ternary representation, we drastically simplify the representation of the numbers as having either a -1 or 0 or 1. Okay, so we just limit the possible numbers of each element in our model parameters as these three numbers, -1 and 0 and 1. Okay, so in this case, how many bits do we need to represent these three numbers? We only need so we have a sign bit over here, and then for this number which is an actual value is either 0 or 1. So in that case, we can represent this three different numbers. So we basically need only like 2 bits to represent each of our elements in our matrix multiplication, I mean our model parameter. So in that case, we can achieve like the much smaller required memory size to store all the parameters in our model, okay? Because we only need 2 bits to represent a single number. And then also when multiplying this matrix vector multiplication, and then the multiplication can become much simpler because suppose our vector is maybe 3, 8, and -4, and then if each of these elements are either 0 or positive or -1, and then if it is 0, and then it means that we can just ignore this value or exclude this value in our computation, and also if we use a +1, and then +1 times this 3 will just give you the original input value of 3. So in this case, we don't actually need to perform the actual multiplication, because if a particular number is multiplied by 1, and then we can just make the same value as an output. So we can bypass the multiplication in that case. Okay, so it's like this. So we have like these 3 numbers as an input, and then suppose our ternary representation of our model parameter as 0 and -1 and 1, for example, and then in this case we ignore it, and then in this case we put the negative sign, and then we put the positive sign, and then just add together. Okay, so that's it. So some subset of addition or deletion of these numbers. Okay, so in this case, if we use the fixed point in this case, the multiplication is completely gone, and then all the operations will be just addition and the subtraction. And so in that case, this kind of fixed point representation may be much more suitable with this addition or subtraction only based computations. So that is one one interesting way to drastically simplify the possible numbers into those 3 numbers in the context of a neural net. Okay, so so in the title page of our slide, it is saying, IEEE standard, right? So in this case, let's see. Okay, so when representing some numbers using the particular number of digits, for example, 32 bits in total or 64 bits in total, and then we predefined the number of bits to allocate to represent the significant or exponent values. Okay, so in this case, the IEEE standard specified the single precision as one of the floating point representation, which allocates 24 bits to represent this significant, and then 8 bits to represent this exponent. Okay, so this is one way, and then also when using the 64 bits, which we also call this double precision. And then in this case, we use 64 bits to represent a single number, and then these 2 numbers are the assigned or allocated number of bits, to represent a single number. Okay, and in this case, we also specified some special cases in our standard. So in the case of a fixed point representation that has this finite ranges, and also this floating point number representation will also have this finite ranges. So in that case, how can we represent negative infinity or positive infinity? So in either cases, it is impossible to represent these 2 numbers, right? So yeah, it is often the case that we need to represent this positive or negative infinity, right? And so these numbers are also assigned by using some specific representation of our bits. So for example, suppose we have a positive sign bit over here, and then we have a significant number bits, and then exponent bits, and then when representing it as all ones, right? So in this case, it will have its own representation when using floating point number or floating point number representation, right? So yeah, we know how to represent this, right? So yeah, in that case, it will correspond to a particular finite number. But when a particular number is represented as in this manner, which represent the maximum possible number that we can represent in our floating point number representation, and then we just agree that, or we just decide that this number is representing the positive infinity. Okay, so in this case, suppose this guy is the corresponding maximum possible value that we can represent by using this floating point number representation, but we just sacrifice this value. Okay, so we decide not to represent this particular number, but when a particular number is represented corresponding to this digit, this particular value, and then we just assign this corresponding value as a positive infinity. Okay? So that way we can have an additional kind of notation when having this maximum possible number, and then we just regard it as a positive infinity. Okay? And also there are several special other special numbers, like this kind of not a number. Okay? And also we need to represent some of these imaginary numbers and so on. And so there are those special kind of numbers that we assigned by specifying a particular representation in the middle of this floating point representation. Okay, and especially this not a number or NaN is quite important. Important number. So it is becoming. I mean, it typically is generated by. It is typically generated when we divide some number by 0, right? So if we divide some number by 0, and then our computer will represent that number. I mean, in that case, our computer will not try to compute that number because it doesn't make sense to divide some number by 0, and then in that case it just directly generates the output as this not a number, and that also that number is also assigned as a special bit arrangement in our floating point representation in IEEE standard. Okay, so any questions so far? Okay, then for this part, I will skip this part because it's too much of a detail. And let's see. Okay, so here we see a specific representation in the case of not a number and positive infinity and so on. Okay, and okay, so in the case of this double or single precision floating point representation, this is the standard, right? But can we also use this fixed fixed point representation in our computers, like maybe Intel or AMD based CPUs that just to support a floating point representation by default. So when specifying our variables, for example in C++ or Java, and then if we use maybe double x, and in this case I believe this x is represented as this double precision number, and using this floating point representation, right? But how can we specify, or can we define the variable that is represented as the fixed point representation in our computer? Okay. Can we have an option to represent the number as the fixed point representation in our computer? So in that case, it is quite simple. So instead of using this, we can just use this int x. Okay. So this can be viewed as just a fixed point representation. Okay. So this is just an integer, right? And so what will be the difference from this integer representation and also the fixed point representation? So in that case, so you guys know, understand this fixed point representation, and then if we use just an integer value, and then if we use this 10 bits, for example, and then typically the integer number will assign all of these 10 digits to represent just an integer. And here in this case, we can kind of consider this case as having the decimal point just over here, right? Just over here. Okay, so we use this fixed decimal point position over here, and then decide not to assign or allocate any bits after this decimal point. So that is the integer variable representation, right? And in this case, how can we kind of represent or convert this integer as having the fixed point representation that has the decimal point over here? Okay, so in that case, we can just compute this integer x, and when representing this integer x, we can actually we can actually compute or convert this number by 2 to the power of -3. So in this case, instead of having this fixed decimal point over here, this number is corresponding to the fixed point representation that has the decimal point located over here, right? And then the rest of the story, when adding or multiplying or subtracting or dividing between these two numbers, will be exactly the same, right? So once computing some values, and then we just do some simple post-processing of this guy. Okay. So in that case, our integer type variable is just an just works equivalently as just a fixed point representation. So sometimes this fixed point arithmetic is called integer arithmetic. Okay, so again, the integer arithmetic is the same as the fixed point arithmetic. Any questions so far? Okay, I think that's it for this floating point representation. And although there are some more details in this slide, but I think that's enough for for this part or this lecture. Okay, so let's take the break for 10 minutes and then resume at 11:50.
픽스 포인트에서 곱셈을 할 때가 더 연산이 효율적이라는 건가요? 아까 말씀하신 게 제가 처음
네.
들어서.
네. 그 픽스드 포인트에서 곱셈을 할 때는 그 디지트를 이렇게 그냥 갖고 와서 그러니까 이게
이거 빼고 디지트로 연산한
네네네.
다음에
그러니까 네 맞아요. 그러니까 요거를 빼고 그냥 그 숫자들을 갖고 와서 곱셈을 하고
점만 찍으면
그렇죠. 디짓 여기 점을 어디에 찍을지는 나중에 그걸 결정하면 된다는 거죠. 근데 그러니까 그 저기 플로팅 포인트에서는 그거 두 개를 그냥 더하면 그냥 되는 거고 여기서는 이제 그 플로팅 포인트 그 포인트가 이렇게 딱 픽스된 곳에 있고
신경 쓰지 않아도 되니까.
네 신경 쓰지 않아도 되는데 그 나중에 이제 어딘가 이렇게 정확하게 찍어주긴 해야 되는 거죠. 근데 그 부분은 실제로 우리가 곱셈을 할 때 드는 연산 뭐 이렇게 다 이렇게 캐리아웃 그러니까 올리고 뭐 이런 연산들에 비해서 훨씬 쉽기 때문에 그거는 이제 차이는 이제 거의 없다는.
그래서 보통 그래서 연산이 낮은 디바이스에서는 픽스 포인트 연산을.
네. 더하기나 이게 여기 뺄셈은 뭐 이렇게 옮겼다가 뭐 이걸 안 해도 되니까. 네.
그래서 제가 아까 이번에 이건 어떤 걸 레프레젠트한다고 봤는데.
이거는 이제 그 컴플렉스 넘버.
그리고 여기서 이게 M이라는 게 뭘 의미하는 거죠? 그러니까 이거 줄의 레프레젠테이션의 차이가 다 똑같은데 M에서 차이가 나는 거잖아요.
네네. 요거 요 두 개 간의 차이요?
난이랑 이 뭐냐
인피니티.
네.
그러니까 이제 이거는 그러니까 이렇게 그러니까 뭔가 우리가 약속을 했다는 거거든요.
네.
그러니까 이게 M이라는 게 이게 익스포넨트고 이 M이라는 게 그 저기 시그니피컨트 그쪽에 이제 그 나타내는 숫자거든요. 그러니까 여기서도 보면 이게 사인이고 여기가 1이 고정이 돼 있고 이 밑에 숫자들이 그러니까 기본적으로 유효 숫자예요, 저 M이. 네. 그래서 그 유효 숫자와 저 익스포넨트
그 줄을 이렇게 다르게 표현을 하는 거예요.
네. 그러니까 이 숫자일 땐 이걸 난, 이 숫자일 땐 이걸 인피니티로 표현을 합니다.
네, 알겠습니다.
Okay, let's continue. So in the next lecture, so we study the notion of condition number. So condition number is defined on a some differentiable function, and it represents some some intuitive like stability, the notion of the stability of our algorithm. Okay, so how can we measure the stability of our algorithm, or our function f? And the stability is defined as this condition number, and that condition number is defined in this manner. So we have a function f, and then we are given the input value x, and then so in a simple case, suppose x was 3 and function value was 8, and if we add, or if we change slightly the input value x of 3 into maybe 3.1, and then suppose our function value has changed as maybe 8.5. Okay, so in this case, the condition number in this particular case is defined as the ratio between the difference of x and the difference of y, or f of an x divided by the difference of the input value. Okay, so in this case the condition number is 5. Okay, but what if our input value x is a vector? Okay, in that case, so this is our input value, and like this. Okay, so in this case, because we now deal with a vector that can have a multiple different directions, right? And then we can measure the amount of the difference in terms of the vector length of the difference. Okay, so in this case, starting from this two-dimensional point of 3, 4, and then we think of various directions of creating this difference from this input vector, and then the output may change, like in the case of 3, 4, then if we add 0.1 and 0, and then it may change the output as 8.5, and then 3.4 plus like this, and then it may change the output as 8.7, right? So in this case, we can kind of measure the length of the function difference between these two, between this, and the original value and this guy. Okay, so in this case, this guy will create a larger difference in terms of an output. So in this case, we choose the direction such that this direction is creating the maximum possible differences in our output, right? So this is the meaning of this soup operation, or this kind of max operation here. Okay, so we actually saw this kind of definition in the previous lecture, which is called induced norm, right? Induced matrix norm. So what was the induced matrix norm? So induced matrix norm is defined in this form. So we want to define some of these matrix norm through our induced vector norm, and then so it is defined in this manner, right? And then if it is a 2 norm, and then we just put the 2 norms on both of this denominator and the numerator, right? And if it's 1 norm or infinity norm, we can also define that accordingly. Okay, so it is almost similar to this guy, but we do not restrict our function f as this linear transformation with the given vector x, but we consider this general vector general function f, which is not necessarily linear. Okay, so in that case, yeah, it is in general. This condition number is now represented as this Jacobian matrix. So how this Jacobian matrix is defined as follows. So in the case of the Jacobian matrix, we now consider the input is a vector and the output is also a vector. So like in this case, so we send m-dimensional vector to n-dimensional vector as an output, and this transformation is not necessarily a linear. So in this case, the Jacobian is defined as follows. So let's think of this three-dimensional vector into maybe two-dimensional vector. Okay, and in this case, if our output is a vector, and then we can just think of these two output element of an output separately. So for example, in this case, maybe 2x1 squared and 3x2 plus 5x3 plus 4. Okay, so that can be one definition, and then y2 can be negative x1 something like this. Okay, so we can think of these two separate functions like this, and then yeah, in case of this scalar output, and then we can define its gradient, okay, which is a vector or column vector composed of the partial gradient with respect to our input variable x, right? So in this case, what is our partial derivative with respect to x1? So in this case, 2x1, and that's it, right? And then in the case of partial derivative with respect to x2, and then it is like 3 and 5. Okay? So that will be our gradient vector. And then we can also think of the gradient vector over here, and then negative 1 and 3x2, no, 6x2, oops, over here, it should be 4x1, right? Because we take the derivative of this term. Okay, so here 3x3 squared, right? So this is another gradient vector with respect to, yeah, for this second element in our vector form of an output. Okay, so in the case of Jacobian, we just simply merge them together as a single matrix, where our Jacobian is now defined as like the row vector, transposing each of our gradient into this row vector, 4x1, 3, 5, and negative 1, and 6x2, and 3x3 squared. Okay, so this is our Jacobian matrix, which means that the first column is composed of the partial gradient of the first element in our output vector, and then with respect to each of our input variables, right? So in this case, the Jacobian matrix has the size of 2 by 3. Okay, so this is the Jacobian, and then in the case of this condition number, definition of this condition number, and then it is actually defined as this norm of this Jacobian matrix. Okay, so in the case of the let's see. So what's the meaning of this Jacobian? Okay, in this case, suppose our initial input of x1, x2, x3 were maybe 3, 4, 5. So that was, suppose that was our current input value, and then this Jacobian matrix is indicating or representing the partial derivative at this particular point of this 3, 4, 5 as an input point, right? So in that case, along the x1 direction for the first output, and then the partial gradient will be just to multiply, just combining those, plugging this value into over here, right? So it's like 12 and 3 and 5. So these two are constant, right? And then we just plug this guy into over here, and then -1 and 24, 75. Okay. So this is the collection of the partial gradient with respect to each input for each output, right? And then this one tells us how fast the output is changing with respect to the unit unit changes, or the small changes in terms of each of our input value, right? And so intuitively, the norm of this matrix, okay, the norm of this matrix, will define how much we can make how much changes we can make in terms of our output by changing the small by making the small changes in our input. Okay, so even though we didn't specify a particular norm here, whether it is a 1 norm or 2 norm or infinity norm, but you can just have this kind of intuition of the meaning of this Jacobian, okay? And then manipulating this Jacobian matrix, for example, when thinking of this Jacobian matrix norm, and then we will just specify the direction that will kind of maximizes the resulting vector norm, or this induced norm of using this Jacobian matrix. Okay, so that will be the maximum possible amount of the difference in terms of our output with respect to the input. So that's how we kind of relate this Jacobian with this condition number. Okay, and then this is called the absolute condition number. And now we are more interested in this relative condition number. Okay, relative condition number. So the relative condition number is defined as like the relative, the ratio of the relative changes with respect to the y value, and also the relative changes with respect to the x value. So in this case, so in this particular case, so I just gave you kind of a simple example of how we compute this absolute condition number, which is just the ratio of the difference with respect to x and the y value, right? But when computing this relative condition number, this computation is changing in as follows. So we consider the relative change in terms of an x, okay, and then that is like 0.1, which is the difference of an x, divided by the original x value. Okay, so that is corresponding to this part. And then the numerator is also the relative changes with respect to y values. So 0.5 is our changes of our y value, but it is actually divided by the original y value in this part. Okay, So this is the definition of this relative condition number, and yeah, we can actually see the form, yeah, the notation in this form. So this is the relative changes of an x, and this is the relative changes of y value. Okay? So the ratio between these two is defined as the relative condition number. And then if we rearrange them, okay, if we rearrange them, and then we can represent it in terms of the absolute condition number. So in this case, so we chose this guy and this guy, okay, and then bringing them out in this form, and that becomes our absolute condition number, right? And then what about the other part? The other part is represented as like this form, right? Okay, so it is defined as the absolute condition number divided by the ratio of the original input and output. Okay, so this is our relative condition number, and its relationship to the absolute condition number. And then we represented this guy as our Jacobian matrix. Okay, and then once obtaining this Jacobian matrix and its norm, and then we divide it by this relative ratio of current input and output. Okay. Okay, so yeah, let's use some of the example. So here, let's just use a simple example of this a times x, where we send a one-dimensional input to another one-dimensional output. Okay, so in this case, if we compute the Jacobian, and then it is computed as an alpha, right? And then this is our absolute condition number, right? But what about the relative condition number? And then the relative condition number is actually dividing this absolute condition number divided by this ratio of an input and output, right? And so relative condition number is computed as 1, right? So it's like, so if we consider maybe 3x, and then suppose our current input is 2, and then the output will be 6, and then if we change it to 2.1, and then the output will be 6.3, and so the relative difference, or the ratio between the input difference and the output difference is like 3, right? But this 3 should be additionally divided by like those input and output ratio of 3, right? And so we have 1 over here as our relative condition number. Okay, so we can also think of this additional function, another function of square root of an x, but I'm gonna skip this part and then move to the next example of this guy defined as x1 minus x2. So in this case, we are considering the function that sends two-dimensional input to one-dimensional output, and then let's consider it's a Jacobian. So in the case of this Jacobian, because our output is just one-dimensional, so our Jacobian is just a transpose of our gradient. So our partial derivative with respect to each of an input variable is 1 and minus 1. And so this guy, 1 and negative 1, is our Jacobian matrix. Okay. And then let's consider this infinity norm, induced norm by using L infinity norms. So in this case, how do we define this L infinity norm? L infinity norm is taking the maximum value, right? Maximum value. Okay, but in this case, what is the induced norm of this matrix? Okay, so in this case, we can just carefully manipulate this input vector or the two-dimensional input vector over here, and then consider its the resulting kind of a one-dimensional value and its infinity norm. And because it is just computing one-dimensional output, and so L infinity norm or L1 norm or any other kind of LP norm will give just the same result. And so we can just select or choose some particular input vector that will maximize the resulting value. Okay, so in this case, satisfying the L infinity norm as 1. Okay, and then we can choose such a two-dimensional vector in this manner. So we can just set it as 1 and -1. So in this case, what is our L infinity norm? And L infinity norm of this two-dimensional case is just 1, for example. Okay, so in this case, we chose this vector, and then in this case, our induced norm of this Jacobian matrix will be just a 2, right? So in this case, we can see that this 2 is our absolute condition number. Okay, absolute condition number. Okay, and then now let's think of this relative condition number, which is further dividing this number by the current ratio between input and output. Okay, so in this case, let's see. In this case, let's think of this case where x1 and x2 is almost the same. Okay, so in this case, x1 is maybe 1.1 and x2 is 1. So in this case, what is our output? Our output is 0.1, right? Okay, so in this case, this a function norm of an output which is just a one-dimensional vector will be just 0.1, right? But what about this norm of an x? So the norm of an x, in the case of an infinity norm, it will be still like 1.1 or maybe close to 1, right? So this is some number close to 1, but we can actually we can observe that this f of an x and its norm is close to just 0, right? So if our current output is close to 0, and then for whatever changes made to our outputs, and then the ratio, if we think of this relative norm intuitively, and then so here we see this is the norm of an input vector which is close to 1 currently, and then we created some changes in terms of our input, but here the most important part is this guy. So this guy is close to 0 because our current output is 0, close to 0 or 0.1, for example, right? And so for whatever changes made due to the changes of an input, and then because this denominator in terms of this original y value or output value is really small, and thus this value can actually explode into really large value. So that is the intuition that, yeah, in this particular case, the relative condition number can actually explode. Okay. Okay, so in that case, the relative changes of an y can become really large. Okay, when changing the x relatively small. Okay, so that is the meaning or some interesting characteristics when considering this relative condition number. Okay, so yeah, when using this function, although it looks quite simple, which is an x1 minus x2, but even for this really simple cases, when considering this relative condition number, and then this function can be kind of unstable, which means that the relative changes of an output can become really large, okay, for a particular input value. Okay, so that is, that happens only when the current output is close to 0, right? 네.
자코비안 세 번째 에그램플에서
네.
자코비안의 놈을 구할 때요.
네.
저게 인피니티 놈으로 계산하는 건가요?
네, 지금 여기에서는 그렇게 하고 있어요.
인피니티 놈은
네.
벡터에 대해서 인피니티 놈하면 가장 큰 요소의 절대치만.
네.
그다음에 저건 1 아닌가요?
그게 이제 벡터에 대한 인피니티 놈이고요. 그러니까 이제 so the question is, when considering this Jacobian as just literally a vector, and then its infinity norm could be just 1 because we are taking the maximum value, but we consider the matrix like induced norm. Okay, so in this case, the induced norm is defined as it is defined as follows, and so our A currently is 1 and -1. Okay, so let me just clarify why we need to consider this Jacobian and its matrix induced norm. Okay, when considering this relative, the condition number. So here, so we now, at this point, we understand the meaning of the Jacobian, but why this condition number like this should be represented as the Jacobian of, the norm of the Jacobian, or more exactly, matrix induced norm of Jacobian matrix. Okay. So in this case, in this case, it is based on some of the first order approximation. So what that means is, suppose we are given this f of an x, which is not necessarily a linear, but this linear, nonlinear function, potentially nonlinear function, can be approximated at current input vector x, which indicates a particular input value or a particular point in our function, right? And in this case, it is represented as f of an x plus Jacobian times x. Okay. So this is a Taylor expansion or approximation. So does it make sense? Oh yeah, so here I need to write it in this form. So here Jacobian is also a function of our input vector, just like this form. So this is our Jacobian, and this is of course a function of the current input, right? And that tells us the first order derivative, or how fast it is increasing. I mean, the first component or the first output element is actually like having the increasing rate of 4 with respect to the input value x1, and with respect to x2 it has the constant ratio and also the constant increase ratio, right? And so yeah, in case of like this kind of input, particular input of 3, 4, 5, and then what will be the partial gradient of each output value, and then as I mentioned, like yeah, we have this partial gradient or the Jacobian matrix output. And so in this case, yeah, suppose we currently have this kind of mapping of like 3, 4, 5 as an input and 7, 8 as an output vector. So suppose this one is current input and output mapping. Okay, and then f of an x when x is 3, 4, 5, and that particular point or position, yeah, even though this f of an x has a really complicated curvature in our function, but it can be approximately represented as this 7, 8 plus our Jacobian matrix, where x is plugged in with this 3, 4, 5, which is so this is the current Jacobian matrix at this particular input, right? And no, so this shouldn't be something like this. Does it make sense? So this is a current output, and then this is the first order approximation of our function in terms of this linear increment with respect to the delta value, or the increment with respect to input, and then what amount of an increment does it make in our output. So that is computed in this form, right? So for example, 3, 4, 5 actually change it as 3.1, 4.1, and 5.1, and then 0.1, yeah, is actually the increase, right? And then this is indicating the ratio of the y increase with respect to x increase, right, at this particular point. And so this is the increment, and so yeah, so we just plug in or just multiply them, and then we just compute we just compute the total increment of y with respect to each of our increment in our input. So does it make sense? It's just a Taylor expansion or approximation, or this guy is not, it can be also alternatively represented in this form. X minus, let's call it as an x1, and so this is x1, right? So x is our value, x is an arbitrary input, and then this indicates the difference of this guy from the original starting point of an x1, right? And then this is the linear kind of approximation, or the constant increment computed at this particular point of 3, 4, 5, and then by multiplying the increment with respect to x, then we can represent this f of an x in this. Does it make sense? 이거 이해 가나요? 가는 사람, 안 가는 사람.
맨 위에 있는 근식이 아예 좌항에
이거요?
좌항에 있는
이거 여기 돼야 돼요? 네.
아예 fx 다 x는 x.
네.
이게 뭘 의미하는 건지.
이거요? 오케이. 네. So what is the Taylor expansion or approximation? Suppose we have some function. I mean, let's just simplify the case as a one-dimensional function like this. So which maps R1 to R1. So suppose our current input is 3, and then output is, for example, 2. Okay, and then at this particular point, and then just like kind of a gradient descent, let's think of like just the enlightening, or like yeah, we can only see the part of our function near the current input of 3 or 3, 2. Okay, and then what will be the first order approximation of this complicated function, and that function will be like this guy, right? So this is a first order approximation of this function evaluated at the current point of 3, 2, right? Okay, in this case, how can we represent? Okay, so let's think of this function as like 3x yeah, let's think of this kind of function, and then we are currently at 3, 2, and then the first order derivative of our this function is, so this is a kind of a approximated function evaluated at x being 3, and then in this case we can represent it as like this point. Okay, let's call it as an x1, and it is like x1, which is 3, and then plus f prime x1 times x minus x1, or delta x. So far, does it make sense? So it is the point, indicating 3, 2, because when plugging this x1 into f, and then it will create 2, right? Okay, then this is the difference. So in this case, this is particularly a linear function of x. So this is only the variable that we have, and f of x1, which is a constant, right? And also f prime x1 times x1. So this is also a constant, right? And then plus fx1. So whole part of this is the constant. right? So it is like approximating a function as ax plus b, right? Okay, and then yeah, let's just plug x using a different value. So if x is 5, for example, and then we have 5 over here, and then our approximated function value will be over here, right? And then how do we compute this value? So we start from 2, which corresponds to here, and then here at this particular point, the increment or the partial derivative or the ratio of this increment upon y with respect to the increment upon x is what? Let's compute it. F prime x is 12x squared and 2, right? And so if x is 2, and then f prime 2 is 50, right? And so at this particular point, as we increase the x by 1, or the unit length, and then the y will increase by 50, right? And so what if we are given the input value as 5, and then it's like, so we change it by like 2, right? And then we just simply apply the ratio of this increment upon y, right? And so 50 by 2, which is 100, and then we add this 100, from this 2, right? So this is 2, and this is the increment when given an arbitrary x value. It can be 5 or 6 or 7 or maybe -1 or any value, right? And then we just compute the increment with respect to the original x value of 3, right? And then we just multiply that ratio of this gradient evaluated at that particular x1. So does it make sense? So this is the Taylor expansion, or the first order Taylor expansion, right? So the main idea is over here. So starting from this position, when approximating some output at an arbitrary value, and then we just compute the delta value, and then we just simply multiply it with the gradient value that actually indicates the slope, or the ratio of the increment of y with respect to the increment of an x, right? So it's a vectorized. It's a vector version. Is actually the same as this form. So we consider the arbitrary input vector, but now we have this particular input-output point. Okay, so this is f of x1, right? And then what is this? So this is our f prime of x1, right? So that is computed as this Jacobian, where we plugged this x1, okay, where we plugged x1 into this Jacobian function. Okay, so that is a function of an x, and then we plugged it in with the current input value, right, with the Jacobian, and then this is our actual Jacobian output, and then this guy is represented as x minus x1, which is like a 3-dimensional vector, and also 3, 4, 5. Okay. So the difference due to x1, x2, x3, so they will be accumulated by using this linear combination, linear combination coefficient. Any questions so far? Okay, so in this particular case, let's just plug this first order approximation into this form. So how do we define this delta f? So delta f is something like this, right? So we have a new point that has the difference of delta x from the original x, and then just to subtract fx, right? And then what is our fx? Approximately, yep, I mean, yeah. So here x is, yeah, suppose x is fixed as 3, 4, 5, and then this one is 7, 8, as I mentioned over here, like this, right? And then given this first order approximation, and then subtracting this 7, 8, which correspond to this part, right? And suppose this guy is a first order approximation, and then subtracting this original output value, and then what's left? The remaining part is just this one, right? So when applying this first order derivative, I mean first order approximation into the original function, and then this delta part, or this delta f, is now just simply represented as the Jacobian matrix times the delta x, which is just a linear function. Okay, and then now and then we have a Jacobian matrix corresponding to this part, right? And then now when considering its matrix induced norm, or the maximum difference that we can create by carefully changing this delta values, and then we can just apply the matrix induced norm over here, right? Any questions? So that's why we see the norm, or the matrix induced norm of this Jacobian matrix over here, due to the first order approximation. And then back to the original question of the student. So here, let's see. We now consider, in this case, our Jacobian matrix is 1 and -1, right? So regardless of any input, the Jacobian matrix is fixed as this point, right? So over here. Okay, so here we have to consider is a matrix induced norm of an L infinity norm, and then we consider, let's call it A, and then AX. Max. Okay, so in this case, let's also, we can also think of like this. Subject to okay, so we have a freedom to choose any vector that satisfies its L infinity norm as 1. And then we want to maximize the matrix induced L1 norm, right? So in this case, 1 and -1, and then we want to multiply these two numbers, two vectors, and this vector should satisfy this, and then let's call this as A and B, and in this case A minus B, right? And then now we have an scalar value, and what is the L infinity norm of the scalar value? So we have to take the maximum value, but we only have a one-dimensional output, and so it is just like this guy, right? Okay, so in this case, let's carefully choose x such that it's L infinity norm is 1, and in this case, this A and B can be chosen as 1 and -1, so that it creates 2. So for example, 1 1 has 1 or -1 has is one particular point that still satisfies this L infinity norm being 1. Any other questions? Okay, then now let's think of the condition number of a matrix vector product for our function. So now we restrict our function as this matrix times vector. Okay, so in this case, I mean, we don't actually need to approximate it as a Taylor, as a first order approximation, because it's already one-dimensional function, right? It's a one-dimensional function, and also in the case of this, first order function, not a one-dimensional function. So it's already like y equals ax, right? So in this case, if we compute the first order approximation of this function, and then it will become the exact same function as the original function, right? And then also, what is the Jacobian of this function ax? So a is 1, 2, 3, 4, 5, 6. Then the current input x1, x2, x3. So this is our the function definition, and then the first output is x1, 2x2 plus 3x3, and then taking the partial derivative with respect to x1, 2, 3, and then it will just give us 1, 2, 3, and 4, 5, 6, and thus you guys can see that the Jacobian itself is the original matrix A over here, right? And so when considering the relative condition number, which we often call kappa, and in that case, the Jacobian matrix and its norm divided by the ratio of current output and input, right? Okay, and then this Jacobian is changed into the norm of, the original matrix A, and so we consider it's a matrix norm. And then what is this part? Fx, f of an x is defined as a times x, right? And so changing this denominator as a multiplier, then we can see this as additional part. So so this part came from here, right? And then now let's just manipulate it in the following form. So it's a really rough kind of sketch, rough proof, which is not perfect, but let me just let me show how to manipulate it. So let's call this ax as y, and then even though A has to be in square matrix and invertible matrix, but it should require such kind of condition, but let's just assume A is a invertible, and then x is represented as A inverse times y, right? Yeah, if A is invertible, and then over here it is represented as like A inverse times y, and then we can apply some inequality called the Cauchy-Schwarz inequality, So there is a what is the Cauchy-Schwarz inequality? So let's think of the two vectors of a and b and x comma y, and this is completely separate example. And so Cauchy-Schwarz inequality is like 8 times x plus b times y squared is less than or equal to a squared and b squared and x squared plus y squared. So using this generalizing this Cauchy-Schwarz inequality, we can actually represent like, let's call this as a vector A maybe C and Z. Okay. In this case C transpose Z, and we can see that the left hand side is represented as this guy, C transpose Z, and its norm, right? And then it is now it's a squared, of course, and then it is now represented as a C norm squared and Z norm squared, right? So from here we can generalize this guy into this form. So A inverse y and its norm is now represented in this form. So it's really rough, and it's not kind of rigorous like a step-by-step procedure that I showed, but when considering the norm of this matrix vector product, and then the norm of this matrix vector product is always less than or equal to the product of the two norms of each matrix and vector. Okay, so that comes from this Cauchy-Schwarz inequality, but I'm not going to give you the rigorous proof. But here the point is that given this x norm, and then we can change it into this form, and then can now represent it in this form. Okay, but here when changing this guy into this form, we need this inequality sign, right? And then this y is represented as a times x, and so we can just change this part as y, right? So we can cancel this out between this guy and this guy. Okay, so I changed this part into this, and then we canceled out those two, and then the resulting part is a norm times a inverse norm. So it's a bit it's a bit unorganized, but this is our kappa value, or relative condition number. And then here we decompose this x into these two by just introducing this inequality, and then by decomposing these two, it can be just cancelled out with the denominator part, and then the resulting equation or resulting representation is shown in this form, right? And so our kappa is less than or equal to the product of the norm of these two matrix of an A and the A inverse. Okay, so this is quite an important part. So let's see. this condition, relative condition number is bounded by, upper bounded by this norm, the product of these two norms of matrix A and the A inverse. Okay, and in this case, if we consider this 2 norm, okay, the relative condition number is now using this 2 norm in particular, and in that case, what is the 2 norm of this original matrix A? And in that case, the singular value, the largest singular value of this matrix A, right? Because when considering the matrix induced norm of this matrix A using the L2 norm, right? And then we now, you guys remember this kind of figure. So in this case, we have a freedom to choose whatever direction of a vector, input vector that has a L2 norm, like over here, and then along this particular direction, and then the matrix output, matrix vector multiplication output like this, and then if it is maximized in terms of its length, right, and that length of this ellipse, the largest possible length of this ellipse is actually our L2 norm of this matrix. Okay, and then this length is corresponding to the largest singular value, right? And so this one corresponds to sigma 1, or the largest singular value. But what about the A inverse, the L2 norm of this A inverse? So in the case of A inverse, if we consider the SVD form, so this is U sigma V transpose, and then suppose our singular value was 5, 2, and 1, and then if we consider its inverse, although it is not it's not a square matrix, and so we cannot even think of this inverse, but we can also think of something called the pseudo inverse. So pseudo inverse is simply defined as follows. So so this is not a square matrix, and thus it is not an inverse matrix, but it is not an invertible matrix. But in the case of this pseudo inverse, and then we can just simply take this sigma matrix, and it's taking its inverse of like this. Okay, so we just take the inverse of this each element in our singular value, and that is called our pseudo inverse. Okay. Okay, so it's not a really detailed or organized explanation, but you can intuitively think of this A inverse of so for some particular vector, and then that component is multiplied by 5. But if we consider A inverse, and then that same component is actually multiplied by 1/5. Okay, so in this case, when these singular values are changed into their reciprocals, or the inverse values, and then the maximum value over here is this reciprocal when using this smallest singular value. Okay, so in this case of having singular value of 5, 2, 1, and then this guy will have 5, and this guy will have this smallest one as like this. Okay, so in that case, the 2 norm case can be computed as the ratio between the largest and the smallest singular value. Okay, so yeah, when looking at this form, we can have some kind of intuitive understanding about this. So the singular values will be ordered in a decreasing order. I mean, sorted in a decreasing order in this manner, and then the ratio between the largest and the smallest singular value is 5. And then in some other matrix case, and then that has the largest singular value as 1000, and maybe 20 and maybe 5. Okay, so suppose the 3 singular values are like this from a particular matrix, and then it means our relative condition number in this matrix is like 200, right? And what's the meaning of this condition number or relative condition number? So if we make, again, it's about the original definition of this relative condition number. So if we change maybe 1% of the inputs, I mean in a relative sense, right? So if we change like 1%, and then it's corresponding to like 0.03, and then the relative changes, I mean relative changing kind of ratio in terms of an output can be magnified by 200 times this guy. So our maximum kind of relative changes can be like given this as this number, and then the output, the relative changes of an output. So in this case, 1% of the changes, okay, of an input, and then it can be magnified by 200. And so in terms of an output, it can change like 200% of the relative change of an output. Okay. So the output was maybe 100 originally, and then it can be changed into 300 or negative 100. That creates 200% relative changes. Okay, so that is that is really a bad thing. Okay, so although I didn't give you like a detailed example, but this kind of relative condition number can actually causes some significant, I mean some bad problems, undesirable problems, and then that may kind of mess up all of our computations. Okay, and why do we need to consider this condition number or relative changes or this kind of thing? So this is closely related to our floating point representation. So our floating point representation, suppose our linear transformation matrix was just simply 1/3, right? And then the input was maybe 2, okay? And then suppose this one is our input vector, and this is our linear transformation matrix defined in some of the fully connected layer, although it's just a one node example of an input and output layer. But let's just think of this as simple cases. And then the output should be like this number, and as I mentioned, this number can never be perfectly represented by using the floating point representation, right? Because we have to at some point we have to cut all the non-zero digits, right? At some point, right? So it's like point, so it's infinitely going, right? And then we have to cut somewhere, right? Whether it is a fixed or floating point representation. Okay, so in this case, ideally we want, given this representation approximated in this manner, And then yeah, just moving forward or passing it through another subsequent layer. Okay, so in that case, it should ideally take this kind of input, but inevitably we will have to give this approximated input to the next layer, right? And then if the output is drastically changing due to this small kind of input changes, and then even worse, in our neural net case, the layers will be accumulated, and then this kind of error can be kind of exaggerated. Yeah, it can be kind of expanded more and more, right? So, so that's why we can consider this kind of condition number. So when considering this L2 norm, L2 norm case, and then suppose our neural net over here, and maybe 2, and maybe 3. So we have W1 and W2, right? So in this case, in terms of this relative condition number, the input changes and their amount in terms of its L2 norm, for example, and then this W1 has the singular values, I mean largest singular values of 1,000 and the smallest singular value of 2, and then it has the 5, and then it has the ratio of 200 of our condition number, and then in terms of the relative output, given the true output that we should have obtained, and then we may get like 200% different outputs from the ideal output that we should have obtained, right? And so, and also in the case of W2, it also has the condition number as maybe 5, for example. Okay, so in this case, given a particular input, and then the condition number is 200, and the second layer condition number is 5, and then in terms of the relative changes, and then we can roughly see the condition number just involving both of these two layers as simply like this number. Okay, so that way we can create disastrous or really large output changes when using the matrix that has a bad condition number, which means the large gap or large difference between the between the largest and the smallest singular value. So this is the intuition that you can have in mind about this condition number. And so and then as I think I explained it somewhere in in the previous class, but why does this bad condition number create some of these errors when computing this matrix multiplication? So so if you remember the coordinate changes or changes of this basis, something like this. So given a particular input vector, and then we decompose it into the eigenbasis, right? And then for each of the components along the eigenvectors, and then we just magnify it, or we just scale it with respect to its own eigenvalues, right? And then once they are scaled, in that manner, so we decompose this into these two components, and then along this component we just multiply it by its own eigenvalue of 2 over here, and then along the other component we also multiply it by its own eigenvalue of -1, right? And so for this guy and this guy, it was magnified by 2, and yeah, this guy was magnified by 2, and this guy was multiplied by -1, and then we just add those two vectors together to obtain the final output. Like, yeah, so the final output is over here, and so this is our final output, right? And so what's the meaning of really large gap between the largest and the smallest singular value? I mean, singular value is a eigen decomposition is a special case of our singular value decomposition. So you can think of the exact same scenario in the case of singular value. But so here in this case, along the first axis, it was magnified with a really large amount, like 1,000, and then along the second axis, it just magnified, or it was multiplied by only like a 5. Okay, so in this case, we are increasing the gap, or we are making one component really large, like this, and the second component really small, right? So in this case, when adding these two vectors, and then the resulting vector will be like this, right? And then, how can we achieve this vector addition? I mean, this is a geometric kind of perspective, but when computing it in our computer, and then we would have to represent this as really large vector, like maybe really large value, right? Composed of these two large value, and the second component, second component will be represented as really small value. And then when dealing with these two vectors, we have to add these two vectors, right? And so when adding these two vectors, and then in the previous case of this floating point representation, let's see. So as I mentioned that we have to align those two numbers in terms of their decimal point position, and then we have to add them together, right? But one value is really large, like, so we have all 0 over here, which indicates really large value, and then another value is really small value, like this guy. Okay, so in this case, if we add them together, once adding them, and then we have to cut them, given a particular digits that we can use to represent this significant, right? And so those values will be just ignored, right? So from that process, if we just increase the gap, or if we just make the scales of these two vector components more extreme, like a really large and really small, and then their addition will become more and more inaccurate, right? Because of our floating point representation of using the finite number of bits, right? And so that way the computation will become inaccurate, and that inaccuracy will be accumulated when using that inaccurate vector as an input to the next layer. Okay, and so that's the main source of this inaccuracy introduced in this process, and that is mainly due to really the large gap between the largest and the singular values, because if their gap is really large, and then those two vector, the scales of these two vector elements will become really different. So finite number precision, limit using only the finite number representations, and then it will become more and more inaccurate. Okay, so that is the main intuition of this condition number. And so making this condition number better, which means those two condition number, I mean the difference between these two largest and the smallest singular values becomes smaller. Okay, so that kind of technique is called the spectral normalization. So this is the one kind of regularization technique, quite effective. Yeah, effective in the neural net training process, yeah, especially for maybe generative models and so on. So in this case, yeah, we want to obtain our model so that our neural net. Okay, so we have a neural net over here, and then we have W1 and W2, and for each of linear transformation matrix corresponding to each layer, and then we want to have the singular values, I mean largest and the smallest, the singular value difference for each of W1 and W2 becomes small, right? So what that means is, yeah, we don't want like this kind of pattern of really exaggerating or really multiplying along the one component with really large value, and along the another component it's multiplied with a really small value. So we don't want that situation. So given our matrix over here, and then this matrix should have relatively the same singular values. Okay, so if the largest singular value is maybe 2 and the smallest singular value is 1.5, and then the gap between them will be only 0.5, and what does that mean? It's the largest and the smallest one, and so all the singular values will become almost the same value with each other, right? So that way, along any direction, yeah, we don't exaggerate one particular component that much. We don't want to, yeah, we want to avoid that situation. So that is the main idea of this spectral normalization. And so if we use that, and then we can kind of stabilize more the training process that involves this inaccurate number representation due to this floating point representation. Okay, so yeah, we have some more to discuss on this condition number, but yeah, so the time's up. So yeah, let me just end our lecture here. Okay, and then yeah, we have one more class, I think, before our final exam. Although I haven't gone as much as I expected, but probably due to the English lecture, because of my poor English. So, but anyways, yeah, I'll do my best until the end of our lecture, until our end of semester. So yeah, we will have the exam on the in exactly 2 weeks, on 15th. Is it 15th? But yeah, the Wednesday in 2 weeks. Okay, thank you very much.
The midterms, will we get the results after the finals?
So yeah, I will let you know about the midterm exam scores until next week. Yeah, yeah, certainly before the final exam.